Now that we understand the concepts of atomic number and mass number, the next important step is learning how to calculate the number of neutrons in an atom. Neutrons are one of the three fundamental subatomic particles found inside an atom. They are located in the nucleus along with protons and have no electrical charge, which is why they are called neutral particles. Although neutrons do not carry any charge, they play a crucial role in determining the mass of an atom and maintaining the stability of the nucleus. Without neutrons, many atomic nuclei would become unstable because the positively charged protons would strongly repel each other due to electrostatic forces. Neutrons act like a stabilizing force that helps hold the nucleus together through the strong nuclear force. Since the nucleus contains only protons and neutrons, the total number of these particles is called the mass number. We also know that the atomic number represents only the number of protons. Therefore, if we subtract the number of protons from the total number of particles in the nucleus, the remaining particles must be neutrons. This gives us one of the most important formulas in atomic structure: number of neutrons × mass number atomic number. In mathematical form, this is written as n.do(a)az, where n represents the number of neutrons, a represents the mass number, and z represents the atomic number. This formula is extremely useful because scientists often know the atomic number and mass number of an element, making it very easy to calculate the number of neutrons. Remember that the mass number includes both protons and neutrons, while the atomic number includes only protons. Therefore, subtracting the atomic number from the mass number always gives the number of neutrons. This simple relationship is widely used in chemistry, physics, biology, medicine, and nuclear science. Let us understand this with the example shown in the illustration. The element is chlorine. According to the periodic table, chlorine has an atomic number of 17, which means every chlorine atom contains 17 protons in its nucleus. The example also shows a mass number of 35, meaning the nucleus contains a total of 35 particles, including both protons and neutrons. To calculate the number of neutrons, we apply the formula: neutrons × mass number atomic number. Substituting the values gives 35, 17, $18. Therefore, this chlorine atom contains 18 neutrons. Since the atom is neutral, it also contains 17 electrons, equal to the number of protons. Let's look at another example. Consider the most common oxygen atom. Oxygen has an atomic number of 8 and a mass number of 16. Using the formula, the number of neutrons is 16, 8, counts 8. Therefore, oxygen contains 8 protons, 8 neutrons, and 8 electrons in a neutral atom. Similarly, sodium has an atomic number of 11 and a mass number of 23. Applying the same formula gives 23, 11 × 12, so sodium has 12 neutrons. Carbon-12 has an atomic number of 6 and a mass number of 12, so the number of neutrons is 12, 6 × 6. Now consider another isotope of carbon called carbon-14. Carbon always has 6 protons, so its atomic number remains 6. However, carbon-14 has a mass number of 14. Using the neutron formula, 14, 6 × 8, so carbon-14 contains 8 neutrons. This example demonstrates an important concept. Changing the number of neutrons changes the mass number, but it does not change the identity of the element. Since the number of protons remains 6, the atom is still carbon. Only its isotope has changed. This relationship between protons, neutrons, and mass number explains why isotopes exist. Isotopes are atoms of the same element that contain the same number of protons but different numbers of neutrons. Because the atomic number remains constant, the element does not change. However, adding or removing neutrons changes the mass number. For example, carbon-12 contains 6 neutrons, carbon-13 contains 7 neutrons, and carbon-14 contains 8 neutrons. All 3 atoms are carbon, because each has exactly 6 protons. One important point students should always remember is that neutrons do not affect the chemical properties of an element directly. Chemical reactions mainly involve electrons, especially the electrons in the outermost shell. However, neutrons greatly influence the mass, stability, and radioactivity of an atom. Some isotopes with too many or too few neutrons become unstable and undergo radioactive decay. This is why certain isotopes such as carbon-14 and uranium-235 are radioactive while others are stable. Neutrons also play a vital role in nuclear reactions. In nuclear fission, neutrons strike the nucleus of a heavy atom, causing it to split into smaller nuclei while releasing a tremendous amount of energy. This process is used in nuclear power plants to generate electricity. In nuclear fusion, which powers the sun and other stars, light nuclei combine to form heavier nuclei, releasing enormous amounts of energy. In both processes, neutrons are essential participants. Another important application of neutron calculations is in medicine. Radioactive isotopes are used to diagnose diseases, treat cancer, and perform medical imaging. Scientists calculate the number of neutrons to identify specific isotopes used in these procedures. In archaeology, carbon-14 dating uses the radioactive isotope carbon-14 to determine the age of ancient fossils, wooden objects, and archaeological remains. In environmental science, isotopes help scientists trace pollution sources and study climate change. Therefore, understanding how to calculate neutrons has many real-world applications beyond the classroom. When solving numerical problems, students should always follow a simple sequence. First, identify the mass number. Second, identify the atomic number. Third, subtract the atomic number from the mass number using the formula N_AZ. The answer will always be the number of neutrons. This method works for every element in the periodic table. It is also helpful to remember the relationship among the three quantities. The atomic number tells us the number of protons. The mass number tells us the total number of protons and neutrons. The number of neutrons is found by subtracting the atomic number from the mass number. These three formulas are closely connected. Atomic number Keck, number of protons, mass number Keck, number of protons plus, number of neutrons Keck, mass number atomic number. If you memorize these three relationships and understand what each quantity represents, you will be able to solve almost every basic problem related to atomic structure. These formulas form the foundation for understanding isotopes, nuclear chemistry, radioactive elements, and many advanced topics that you will study later in chemistry and physics. Now that we understand atomic number, mass number, and the number of neutrons, the next important concept is the neutral atom. A neutral atom is an atom that has no overall electrical charge. This happens when the total positive charge inside the atom is exactly balanced by the total negative charge. In other words, the number of positively charged protons is equal to the number of negatively charged electrons. Since positive and negative charges have the same magnitude but opposite signs, they cancel each other completely. As a result, the atom has a net charge of 0, which is why it is called a neutral atom. To understand this concept, let us first recall the charges carried by the three subatomic particles. Protons carry a positive charge of +1, electrons carry a negative charge of 1, and neutrons have no charge at all. Because neutrons are electrically neutral, they do not affect the overall charge of the atom. Therefore, the total charge of an atom depends only on the balance between protons and electrons. If these two are equal in number, the atom is neutral. The simplest rule to remember is this: in every neutral atom, the number of protons is always equal to the number of electrons. This relationship is extremely important because it allows us to determine the number of electrons in any neutral atom simply by looking at its atomic number. Since the atomic number tells us the number of protons and a neutral atom has an equal number of electrons, the atomic number also tells us the number of electrons in a neutral atom. For example, Consider the sodium atom shown in the illustration. Sodium has an atomic number of 11, which means it contains 11 protons in its nucleus. Because it is a neutral atom, it must also contain 11 electrons surrounding the nucleus. The 11 protons contribute a total positive charge of plus 11, while the 11 electrons contribute a total negative charge of 11. When these charges are added together, they cancel each other out. Net charge plus towards zero, therefore, sodium is electrically neutral. The same rule applies to every other neutral atom in the periodic table. Hydrogen has 1 proton and 1 electron. Helium has 2 protons and 2 electrons. Carbon has 6 protons and 6 electrons. Oxygen has 8 protons and 8 electrons. Chlorine has 17 protons and 17 electrons. Gold has 79 protons and 79 electrons. Although the number of protons and electrons changes from one element to another, they are always equal in a neutral atom. Many students wonder why atoms naturally tend to be neutral. The reason is that nature generally favors electrical balance. During the formation of an atom, electrons arrange themselves around the positively charged nucleus until the attractive force between protons and electrons creates a stable structure. As long as the atom neither gains nor loses electrons, it remains electrically neutral. It is important to remember that protons are located inside the nucleus, while electrons move around the nucleus in different energy levels or electron shells. Even though they are found in different parts of the atom, their charges still influence the atom as a whole. The positive charge of the nucleus attracts the negatively charged electrons, keeping them bound to the atom through electrostatic attraction. A neutral atom can become charged if the number of electrons changes. If an atom loses 1 or more electrons, it will have more protons than electrons. Since there are now more positive charges than negative charges, the atom becomes positively charged. Such an atom is called a positive ion or cation. For example, a sodium atom normally has 11 protons and 11 electrons. If it loses 1 electron, it will have 11 protons but only 10 electrons. The total positive charge becomes plus 11. While the total negative charge becomes 10, resulting in a net charge of plus 1. This is written as Na. On the other hand, if an atom gains 1 or more electrons, it will have more electrons than protons. In this case, the negative charges outnumber the positive charges. So the atom becomes negatively charged. Such an atom is called a negative ion or anion. For example, a chlorine atom normally has 17 protons and 17 electrons. If it gains 1 extra electron, it will have 17 protons and 18 electrons. The total positive charge is plus 17, while the total negative charge is 18, giving the atom a net charge of 1. This is written as Cl. An important point to remember is that forming ions does not change the atomic number or the mass number. The atomic number depends only on the number of protons, and the mass number depends on the total number of protons and neutrons. Since gaining or losing electrons affects neither protons nor neutrons, both the atomic number and the mass number remain unchanged. Only the electrical charge of the atom changes. Neutral atoms are extremely important because almost all ordinary matter around us consists of neutral atoms. The air we breathe, the water we drink, the food we eat, the plants around us, and even our own bodies are made primarily of neutral atoms joined together by chemical bonds. These atoms interact through their electrons to form molecules and compounds, making life and all materials on Earth possible. Understanding neutral atoms is also essential for learning chemical bonding. During chemical reactions, atoms usually do not gain or lose protons because changing the number of protons would change the element itself. Instead, atoms gain, lose, or share electrons to achieve greater stability. This exchange or sharing of electrons leads to the formation of ionic and covalent bonds, which are the basis of all chemical compounds. A simple way to remember this concept is to imagine a perfectly balanced weighing scale. On one side are the positive charges from the protons, and on the other side are the negative charges from the electrons. When both sides are equal, the scale is perfectly balanced, just like a neutral atom. If one side becomes heavier because electrons are gained or lost, the balance is disturbed, and the atom becomes an ion. So, always remember these key relationships. Number of protons, sekla, atomic number in a neutral atom. Number of electrons, sekla, number of protons, net charge, sekla, positive charges plus negative charges, sekla 0. These simple principles form the foundation for understanding ions, chemical bonding, electricity, electrochemistry, and many advanced topics in chemistry. Once you clearly understand what makes an atom neutral, it becomes much easier to understand how atoms interact, why they form compounds, and how countless chemical reactions occur in nature and in the laboratory. After understanding what a neutral atom is, the next important concept is ions. An ion is an atom or a group of atoms that carries an electrical charge because it has gained or lost one or more electrons. In a neutral atom, the number of protons is equal to the number of electrons, so the positive and negative charges balance each other, giving the atom a net charge of 0. However, when an atom gains or loses electrons, this balance is disturbed. The number of protons remains the same because protons are tightly bound inside the nucleus and do not change during ordinary chemical reactions. Only the number of electrons changes. As a result, the atom becomes electrically charged and is called an ion. It is very important to understand that atoms do not gain or lose protons during normal chemical reactions. If the number of protons changed, the atom would become an entirely different element because the atomic number would change. Instead, atoms become ions only by gaining or losing electrons. Since electrons are located in the outermost energy levels, they can be transferred from one atom to another relatively easily during chemical reactions. This transfer of electrons is the basis of ionic bonding and many other chemical processes. There are two main types of ions, cations and anions. A cation is a positively charged ion formed when an atom loses one or more electrons. Since electrons carry a negative charge, losing electrons removes negative charges from the atom. The number of positive protons then becomes greater than the number of negative electrons, giving the atom an overall positive charge. In simple words, a cation has more protons than electrons. The illustration shows the example of sodium. A neutral sodium atom has 11 protons and 11 electrons. Because the numbers are equal, the atom is neutral. However, sodium has only one electron in its outermost shell, and it can easily lose this electron to achieve a more stable electron configuration. When sodium loses one electron, it still has 11 protons, but now it has only 10 electrons. The positive charges are now greater than the negative charges. The reaction can be written as Na plus E. This equation means that a sodium atom loses one electron and becomes a sodium ion. The superscript plus indicates that the ion has a positive charge of +1. The atom has not lost any protons, it has lost only one electron. Therefore, the atomic number remains 11, but the electrical charge changes from 0 to +1. Now let us understand the second type of ion, called an anion. An anion is a negatively charged ion formed when an atom gains one or more electrons. Since electrons carry negative charges, adding extra electrons increases the total negative charge of the atom. The number of electrons becomes greater than the number of protons, giving the atom an overall negative charge. In simple words, an anion has more electrons than protons. The illustration uses the example of chlorine. A neutral chlorine atom has 17 protons and 17 electrons. Chlorine needs only one more electron to complete its outermost electron shell and become more stable. Therefore, during a chemical reaction, chlorine easily gains one electron. The reaction is written as Cl plus ECl. This equation means that a chlorine atom accepts one electron and becomes a chloride ion. It still has 17 protons, but it now has 18 electrons. Since the negative charges are greater than the positive charges, the atom has a net charge of 1. The superscript indicates that the ion carries one negative charge. The formation of cations and anions can be understood by comparing the number of protons and electrons. If the number of protons is greater than the number of electrons, the atom becomes a positive ion or cation. If the number of electrons is greater than the number of protons, the atom becomes a negative ion or anion. The electrical charge of an ion depends entirely on the difference between the number of protons and electrons. For example, if an atom has 15 protons and 15 electrons, it is neutral because the charges are balanced. If it loses 2 electrons, it will have 15 protons and 13 electrons. The atom now has 2 more positive charges than negative charges, so its charge becomes +2. On the other hand, if the same atom gains 3 electrons, it will have 15 protons and 18 electrons. It now has 3 more negative charges than positive charges, so its charge becomes 3. An important point to remember is that forming ions does not change the identity of an element. The identity of an element depends only on the number of protons, which is the atomic number. Since protons do not change during ion formation, sodium remains sodium whether it is a neutral atom or a sodium ion. Similarly, chlorine remains chlorine whether it is a neutral atom or a chloride ion. Only the electrical charge changes because the number of electrons changes. Atoms form ions because they seek greater stability. According to the octet rule, many atoms become more stable when their outermost electron shell contains 8 electrons, similar to the noble gases. Metals usually achieve this stability by losing electrons, while nonmetals usually achieve it by gaining electrons. This is why metals generally form cations, and nonmetals generally form anions. For example, sodium is a metal with 1 electron in its outermost shell. It is easier for sodium to lose this 1 electron than to gain 7 more. Therefore, sodium forms a Na ion. Chlorine, on the other hand, is a nonmetal with 7 electrons in its outermost shell. It is easier for chlorine to gain 1 electron than to lose 7. Therefore, chlorine forms a Cl ion. When sodium loses 1 electron and chlorine gains that same electron, the 2 ions become oppositely charged. Positive and negative charges attract each other through electrostatic force. This attraction forms an ionic bond, producing the compound sodium chloride, commonly known as table salt. This is one of the simplest and most important examples of ionic bonding in chemistry. Many common elements form predictable ions. Sodium forms Na, potassium forms K, magnesium forms Mg, calcium forms Ca, aluminum forms Al, chlorine forms Cl, oxygen forms O, sulfur forms S, and nitrogen forms N. The superscript tells us how many electrons have been lost or gained. A positive sign indicates electrons were lost, while a negative sign indicates electrons were gained. Ions are extremely important in everyday life. The sodium and potassium ions in our bodies help transmit nerve impulses and control muscle contractions. Calcium ions are essential for strong bones, blood clotting, and muscle movement. Chloride ions help maintain fluid balance and assist in digestion. Batteries generate electricity through the movement of ions. Electroplating, electrolysis, water purification, and many industrial chemical processes also depend on ions. A simple way to remember this concept is to think of electrons as objects that can be exchanged between atoms. If an atom gives away electrons, it becomes positive because it has more protons than electrons. If an atom accepts electrons, it becomes negative because it has more electrons than protons. The protons remain fixed inside the nucleus throughout the process. So, always remember these key rules. Neutral atom, number of protons tex, number of electrons net charge tecaneurocation. loses electrons, protons, electrons positive charge anion, gains electrons, protons negative charge. Understanding how cations and anions are formed is one of the most important foundations of chemistry. This concept explains ionic bonding, the formation of salts, the behavior of electrolytes, chemical reactions, electrical conductivity in solutions, biological processes, and many other topics that you will study in greater depth as you continue learning chemistry.